Well, good afternoon, everyone. Today is a very good day. This is, in my book, this is the most important day on campus. Happens once a year. And in particular, I think this year, the fact that we're recognizing the person that we are makes it even more special to me. I think he's been through a fair amount of adversity, and it's great to see him here. But I'm skipping ahead here. So welcome to the Arvind Bement Jr. Distinguished Lecture. We had the privilege of naming this lecture and the award that goes with it after one of our most illustrious family members. It's truly a privilege for me to participate in this and to recognize our faculty's achievements. 2016, this year, marks the second year of the Arvind Bement Jr. Award. This award was established by Distinguished Professor Emeritus Arvind Bement and his wife, Mrs. Louise Bement, to annually recognize a Purdue faculty member for recent outstanding accomplishments in pure and applied science and engineering. Arvind Bement Jr. Award winners are nominated by their peers and selected by a faculty committee. We're delighted today to have Arvind Bement with us today in the audience. Arvind, will you please stand and just say hello? So Arvind was most recently the David A. Ross Distinguished Engineering Professor at Purdue. Also in the audience, let's see, are there any other award winners that I'm not going to call them out, but we'll recognize them at dinner tonight as well. It's my pleasure also to invite you all to attend a reception right after this across the hall here in the Robert Ringel Gallery. We'll have a brief reception in honor of our awardee today. And now I would like to welcome to the stage Doraiswamy Ramakrishna, the Harry Creighton Pfeffer Distinguished Professor of Chemical Engineering. As a nominator for this year's award, he will introduce Professor Arvind Varma, the R. Games Slater Distinguished Professor of Chemical Engineering, and former head, till very recently, head of Chemical Engineering, as this year's recipient of the Bement Award.
So it's an absolute pleasure for me to introduce an outstanding chemical engineering academic, an esteemed colleague, and a dear friend for longer than I can remember now. To introduce his background, educational background, he got his bachelor's degree in chemical engineering in 1966 from Punjab University. And then he went over to the University of New Brunswick in Canada, got his master's degree, and moved on to the University of Minnesota, where he got his PhD in chemical engineering in 1972, working under the legendary figure Neil Amundsen. He worked there at Minnesota for a year as an assistant professor, and then joined Union Carbide, worked in industry for a couple of years, and then eventually came to the University of Notre Dame as an assistant professor in 1975. He moved through the ranks. In 1980, he became a full professor, and he was a professor until 1988, then became a distinguished Arthur J. Schmidt professor. He led the department from 1982 to 1988 as a superbly young person leading a department, and hired many outstanding academics that the University of Notre Dame has. In 2004, he decided that it was time for him to do something bigger, and so he came to Purdue University as the R. Games Slayton Distinguished Professor. He also accepted the headship, of which he was Cynthia and J. Eilenfeld, head of chemical engineering, which he did from 2004 to 2016, very recently, he stepped down. He has been an outstanding academic, as I pointed out, and he's won several awards. At the AICHE, he won the Wilhelm Award in 1993. They went on to win the Lewis Award, which is, again, on the side of education, in 2013. Then he also won the award of Chemical Engineering Lectureship of the American Society of Engineering Education, and has won several awards from the University of Notre Dame, Purdue University, that with the charge of finishing this introduction in 2 minutes, I am not at liberty to indulge in relating them all to you. So he has done several, the AICHE award that he won was Wilhelm Reaction Engineering in 1993. And I think that started out a series of other recognitions. He was elected to the National Academy of Engineering in Mexico in recently, I forget the year on which he was elected as a foreign member. He has published 3 books and edited 2 books and more than 300 publications. He has done outstanding work in the area of chemical reaction engineering and material synthesis, combustion material synthesis. And I think that we have here an academic of extraordinary accomplishments. It's a real pleasure for me to introduce to you Arvind Varma, who has, when I relate all the accomplishments as an academic, you would think that this guy couldn't have spent enough time doing administration. But this is where he's also excelled. He has done such a superb job of leading the School of Chemical Engineering, and I must say that at least I should make mention of the more than $100 million that he's raised for the School of Chemical Engineering while he was head. It's a real pleasure to introduce Arvind Varma.
Thank you, my friend. Thank you. Thank you, Remke. Thank you, Suresh and Arvind. I cannot say how pleased I am, and it's very difficult for me to even describe that. The fact that even, I should say how pleased I am to be alive, actually, because it was almost exactly 1 year ago, November 7th, it turned out, last year, that it was discovered that I had pancreatic cancer. The last technical talk I gave was in Shanghai on October 16th. I was on top of the world. I chaired the plenary session for the US Chemical Engineering and China Chemical Engineering Joint Conference. And it was my job to bring the conference together. And that was the day number 5 of the conference. And I was the chair, and I was on top of the world running the show and enjoying my life. Only a few days later, as I was flying back from Shanghai, and it was discovered that I had some problems in my stomach, and I was put through a battery of tests. And to make a long story short, November 7th was the actual diagnosis. Biopsy was conducted. My pancreatic cancer not only was in the pancreas, but also had migrated to the liver, and hence it was in the bloodstream. So therefore, you cannot do surgery, you cannot do radiation. The only thing you can do is a chemo treatment. Fortunately, with some research, as we are all in universities do research, by my own research, and most importantly, through my friendship with a very distinguished chemical engineer who is at Harvard, Rakesh Jain, who is the director of the tumor biology laboratory at Harvard, and also the same laboratory is at MGH, Massachusetts General Hospital. To make a long story short again, he said, Arvind, if I have what you have, I would go to TGen, which is where my own research was also leading to, but I wasn't sure because I was oscillating between them or IU, because it would have been so much easier to do the treatment in Indianapolis and stay home and just go back and forth. So, but thank God I didn't do the easy thing, and I did what Rakesh suggested and what my own research also was leading to. I should say less to my own research than actually to Rakesh's suggestion. And I was so fortunate, and as some of you know, Nancy Ho, one of our faculty members in chemical engineering, got the National Medal of Technology this year, and it was my pleasure to nominate her for that honor. And from Scottsdale, where I was for 7 months for my treatment, I went to the White House to attend Nancy Ho's National Medal ceremony. And interestingly, Rakesh Jain got one of the National Medals of Science this year. So not only was I able to celebrate at the White House with many others, of course, Nancy's National Medal of Technology, but also Rakesh's National Medal of Science. And I was able to thank him personally for really saving my life by his suggestion. I can say many, many more things, but I won't, because I do have to give this lecture. There is a price to be paid for this award, it turns out, and the price is the lecture. And it is a very nice price to pay. There's not a big price at all. I should, before starting though, say a word or two about Dr. Bement. It really is very nice of him and his wife to have established this award. Of course, there is a monetary prize, and more interestingly, let us say maybe more importantly for me personally, there is a small amount of research fund that comes with it as well. So we are always struggling in universities for research funding, and that fund, because also it is indirect cost free, and any other fringe is free. So it permits really to go quite far, the amount that is. So I thank Arvind and his wife for having established that. Arvind, as Suresh already mentioned, is a very distinguished professor of engineering. He was formerly the head of nuclear engineering here, and then went on to have a very illustrious career as the director of NIST for a number of years, and then for 7 or 8 years as the director of the National Science Foundation, before he was lured back for a few years to serve as the inaugural director of the Global Policy Research Institute at Purdue. So Arvind's contributions are legendary, and I'm very grateful that he and his wife established this award, and that my name somehow now is associated with a very distinguished professor of the university, Dr. Arvind Bement. Thank you very much. I think I may have already mentioned that this is actually the very first lecture that I'm giving, very first technical talk since the last one I gave in Shanghai a year ago. So it is all going to be very rusty, but I did look over a few of these things over the weekend and the last few days. So, but still, you have to forgive me if things are a bit rusty, because I can only work so much, it turns out. I'm supposed to be on medical leave, but I still work my 40, 50 hours a week. And it is impossible for me not to, because that sort of defines us. But I am extremely pleased and thrilled to be here. And before I go too much far, and actually, in fact, I start the lecture, I have to thank my wife here, Karen, who's been my wife now for 45 years. It is very clear that without Rakesh Jain, I would not be alive, but it is also very clear to me maybe even more so, that I would not be alive without Karen. She really took such great care of me continuously there and here, and that I am standing in front of you. So let us see if we can get the first slide on. Do I need to? Oh, yeah. I thought I would speak to you about this very general kind of an area, many different kinds of problems related to energy and chemicals with which I have been very fortunate to be involved in. And this involvement, of course, comes through our graduate students and postdoctoral associates and other colleagues. And I have just been fortunate that I was connected with them and some interesting work was conducted. There are 4 parts to this talk. One advantage of creating these kinds of distributions in the outline is that these topics are not related to each other. The relationship simply comes from the fact that they're all in catalysis and reaction engineering. So that is the theme that connects all of these topics. But the other part is that these topics can be, if I, for example, only do 2 out of the 4, that would be fine, because the other 2, they're not related to the first 2. So therefore, there will still be a complete talk. So one can finish this talk in 4 different ways. If I really speak lots of other things and don't talk at all about research, I could do the first topic maybe, and so on and so forth. So the advantage is that one can actually quit any time, and yet it'll be a reasonably complete talk by itself. All of these topics that I'm talking about, they all have been done in my laboratory in the last 5 or 6 years, by the way. They're not very old. They're all very new. Nothing goes back to Notre Dame, nothing goes back. It's all in the decade of 2010, actually. So we are talking about the last 5, 6 years. All of the work I'm talking about. There is not a single publication that I will talk about that goes before that time. So they're all very recent, and it gives me a lot of pleasure to be able to talk about these new things. And the first one of these is the topic that engaged me for a number of years, 5 or 6 years, hydrogen generation for vehicle applications. And here are some of the people who worked with me. There were a couple of PhD students who finished. Moise Dewan, very outstanding person, who joined AbbVie, and now already is leading a group of 25 chemical engineers to lead their chemical reaction engineering and process development group, the entire group. PhD only from about 6, 7 years ago. Brilliant guy. Finished in less than 4 years. In fact, 4 years, I should say 4 years and a month, but he went and did a summer job for a summer for 3 months. So in fact, it was only 3 years and 10 months, starting with a bachelor's degree, that he finished his PhD. And then I was fortunate to have Ahmed Al-Kukun join him, who topped him even. Moise wrote, I think, 6 publications with me in his less than 4-year PhD, while Ahmed wrote, in fact, 7. And to top Moise, he finished in 3 years and 9 months, not even 4. And of course, he did not go anywhere for his summer jobs. Then he went to Intel. He was, I think, the highest paid guy to be recruited by Intel that year. And then a couple of other postdoctoral associates who I had the great pleasure to work with, Yevgeny Shifirovich, who's on the faculty and associate professor now at UT El Paso, and Hunte Huang, who's now an assistant professor at the University of Kentucky. So these 4 individuals contributed to the work I'm talking about in the first topic. The motivation for this work comes, let's see how I can do this effectively. Maybe I will sit down, actually. Maybe I will sit down. Well, so the motivation is that so there was an idea some years ago that we would use hydrogen-powered fuel cell cars. So then the issue was, how will the hydrogen come about? So there are two choices here. One choice is, and this is a diagram that the Department of Energy had produced. So there is what you need for the requirement is these green lines that are here, they define the boundary. You need to be in this region from the hydrogen mass density of your system that's going to produce hydrogen. And as far as the volumetric density should be higher than this number, and the mass density should be higher than this number. So you should be in this part of the region. Now, if you say, okay, fine, let's just use hydrogen inside a cylinder. Well, that's 100% hydrogen by mass. So we are safe, 100% hydrogen, gas is available to us. But it's a gas. How do you use it actually? Well, you got to have it in a cylinder then maybe. Well, by the time you put this hydrogen in a cylinder, if it's 350 bar, that'll be like 5,000 pound pressure. 700 bar would be 10,000 pound pressure. So well, this 5,000 pound pressure brings your weight down to 5% already. So 95% of the weight actually is of the cylinder. Only 5% is of the gas. It's a big problem. So fine, you can use the gas, but how do you contain the gas? That's the trouble. So there are many, many compounds that are listed here. These are compounds whose intrinsic weight percent and volumetric percent is listed. So for example, methane is 25% hydrogen, 4 out of 16. But that's methane by itself. Now, how do you contain it? How do you create hydrogen out of it? Release it? This is a big problem. So therefore, people had been thinking at that time, and there was a large program. In fact, I was very fortunate to be part here. And there was, I don't know if Professor Jay Gore or Ramachandran are here. We were all part of a DOE-funded program that lasted about 4 or 5 years and gave us lots of money and lots of nice papers. So we all worked on, and there were also a number of other people working on in the country, maybe about half a dozen others, chemists and material scientists largely. I think I was the only chemical engineer. So we're working on a compound called ammonia borane. Ammonia borane has 19.6% hydrogen. So if you're going to be having to release hydrogen on board inside a vehicle on demand, you need to start out with a material that has high capacity by itself. Because if it doesn't have high capacity, then what are you going to do? You're already behind the 8 ball, actually. And because you need to, at the end, have this 5.5%, 8%, and the volumetric density is here. So they start with ammonia borane, but ammonia borane is a solid. Now, again, how do you release hydrogen out of it? So you got to make a system out of it. Now, it turns out that there is a rule of thumb in this game, and that is that if you want to make, say, 5.5%, your intrinsic in the solid, the capacity for that solid, for the hydrogen, should be at least twice as much. Because if it isn't even twice as much, then you don't really have any room to play because you have to now make a system out of it, release the hydrogen, and then how are you going to get your 5.5% if you don't even have 11% to begin with just in the material? So having something that has 19% gives you the opportunity to develop a system, and that's actually what we did. So what was known before I started my work, and this before we started the work, was hydrolysis could be done. Hydrolysis of ammonia borane could actually be conducted even at room temperature with the presence of ruthenium catalyst, but it would produce only 5.5%. Where's the starting point? You have something, you need some method. And because remember, the demand is very high requirement on board a vehicle, press the accelerator, hydrogen will come out and off your car would go. So it's not a small demand, it's a high demand. Then the other thing you could do is thermolysis, which is simply heat up the ammonia borane. And it turns out that if you heat it up to about 90 to 117, you get 1 mole out of it. Ammonia borane has 3 moles of hydrogen, 6 moles of hydrogen, so 6 atoms of hydrogen, so 3 moles of hydrogen. So each mole comes out at different temperature levels. So about 170, you can get the second one, but you have to go to about 500 to get the third one out. So these are the numbers, and these are stoichiometries. You cannot violate these numbers. So then you have to make a system out of it. How do you make a system out of it? So what we came up with in my lab was a new process called hydrothermolysis. And the idea of this whole process was that we combine hydrolysis and thermolysis. And I can go through lots of details about why this is needed. So it turns out that hydrolysis can occur in the presence of a catalyst, but actually it can also occur without a catalyst around 70 to 80 degrees C, 70, 75 degrees C, you'll get the first bubbles of hydrogen already. And the interesting thing is that hydrolysis of ammonia borane is exothermic, it releases some heat. So if you could build a system in which you could capture the heat that is being released by the hydrolysis and use it to conduct thermolysis, then you are in good shape. At least you are ahead of the game a little, because you're using part of this heat to conduct that heat. And this reaction is more attractive because it is going to give rise to larger hydrogen percentage. So that was the idea. But how do we make a system out of it and so on? Okay. So we made a system with a hydrothermolysis, and we carried out in a power reactor and demonstrated that as you increase the concentration of ammonia borane in this water solution, you can in fact get more and more and more hydrogen out as you increase the concentration. It was quite a discovery for us. And in fact, in the literature, made quite an impact, a splash, actually, this kind of work. And in fact, we could go up to about 14% out of it. So not only we are making twice of the 5.5%, we are exceeding it. So you need that. And furthermore, it could be done at temperatures that are relatively low. And this is another part of the requirement, that the PEM fuel cell operates at 85 to 90 degrees Celsius. So you need a system which is going to release the hydrogen at the level that we want, amount we want, but also the temperature that we want, because we don't have this higher temperature available to us. Fuel cell only operates at this kind of temperature. So that's where the waste heat is available. So these are all very, very strict requirements in trying to operate in this. So then we also wanted to understand, okay, so good, this is working, but sort of, what's going on? So we did some deuterated water experiments. So instead of taking water, we took D2O. So the thing with D2O is that if you do the hydrolysis with D2O, because it's D, not hydrogen, you will make actually HD. So, but then what you can say is that if you got hydrogen in the system, that actually came from the thermolysis part, because thermolysis will produce hydrogen. That's just breaking up of ammonia borane, that's it. But if it was hydrolysis, since the fact that we are not using water, we are using D2O, we're actually going to get HD. So if I just monitor in the gas phase how much HD versus H2 I have, I can then tell what of this hydrogen came from the thermolysis part, what of the hydrogen came from the hydrolysis part. So I could split up and I could mechanistically understand what was going on. And there is many, many papers that we wrote, but upshot of the whole thing is that as you increase the concentration of ammonia borane, in fact, the thermolysis increases as you would expect. Because you're increasing ammonia borane, so more and more thermolysis will occur, and less hydrolysis will occur. But lo and behold, the combination of the two produces about the same amount, so that you're producing 3 moles roughly, which is all you can get from ammonia borane. So very nice process could be built around this idea of hydrothermolysis. And by the time you come down to full ammonia borane, well then pure ammonia borane has only 3, and because the temperature is less than what you can have for release of more than 1, you're only running at 150, 185 to 120 degrees C. You're only going to get 6.5 out of it. So you see, there is a maximum in the system If you go beyond that, then you're going to go on to ammonia borane itself, which is only 6.5%. So you had a nice sweet spot in which you could create a lot of hydrogen in the system. Very nice. And we did a lot of experiments to understand what was going on. It turns out the hydrolysis occurs first, that little bit of heat that's generated by hydrolysis drives the thermolysis, and they two feed on each other, and then how the process works. Now, there is one fly in the ointment, and that is that whenever you do hydrolysis, you make BO bonds. It turns out by calculations and of experiments, you can show that the BO bonds that are generated by any kind of hydrolysis, they are more difficult to regenerate back into ammonia borane from the spent ammonia borane than the NB bonds that you get out of ammonia borane thermolysis. So it's better to have thermolysis rather than hydrolysis, because then your spent product will be easier relatively to regenerate. So therefore we said, okay, let's think of some other ways now. So we can do it, but the regeneration is a problem, so let's go to some other method of doing it. Because we are engineers, we are chemical engineers, we'll think of different ways of solving the problem. And all we have to do is just be creative enough and have creative enough students and postdocs with us that we can actually do the job. And that is the beauty, of course, of being in a university atmosphere. So we came up with the idea that let's do this. Because interestingly, also surprisingly, in fact, most thermal decompositions tend to be endothermic. You have to provide heat to break them up. Thermolysis of ammonia borane is an unusual thermolysis. It's actually exothermic. The first two releases are exothermic. Third one is not. So you're generating a bit of heat actually even in the thermolysis part. So that's wonderful, because then what you can do is you can say, good, if I could just capture the heat, if I could initiate somehow my thermolysis and I could capture the heat, then maybe I could build up on that heat and be able to do the thermolysis. And lo and behold, that's exactly what we could show. So if we did thermolysis of ammonia borane, say for example at 90 degrees C inside a power reactor, and we are monitoring the temperature of the reactor, which is in black, and of the sample, which is in red, and we're monitoring the hydrogen yield, which is in blue, then if we do no heat management, so to speak, word heat management being used a little loosely, which means just by capturing the heat of the system, then we only get 5% at the end and nothing to write home about. And that's what you expect, because the temperature is only 90 degrees C. You only get the first release at most, not the second or the third. But if you could just put some quartz with some insulation so that there is enough room here for the hydrogen to come out in terms of the porosity of the system and can still leave the system, now you can capture the heat. And indeed, lo and behold, what you find is that when you monitor the temperature, the reactor temperature is in black. It just simply is following here. But the sample temperature, in fact, is the red one. It reaches close to 200, maybe 190 degrees C. So here you have a system that by capturing the heat of the system, the release, you were able to now release 15% hydrogen from this system. Again, much greater than the 11% that you could get otherwise, that you need to get from the system, because you have been able to be creative to capture the heat in the system before it is lost out. So this was one method, but we were not satisfied with just this one method. And one other part of it was that the system has lots of constraints. One of the constraints is that there is some ammonia that's formed in the system. And ammonia, because of the PEM fuel cell, there is a platinum electrode, so that gets deactivated. The ammonia cannot be more than about 10 ppm. You got to be very low on the ammonia. It turns out that, I'll show you a chart in just a couple of minutes, the ammonia formation is very significantly reduced. In fact, you'll find this at the order of 10 ppm. So indeed, we could reach the numbers needed with the heat management system. And then we came up with yet another system, and that was that mix some boric acid, so just have another additive added to the ammonia borane. And what boric acid does is that boric acid begins to decompose around this temperature shown around 100. So, but before that, there is already some water that's liberated around 80, 85 degrees C. And it forms what's called metaboric acid and water. This water reacts with the boric acid itself, the additive, and makes tetrahydroxyborate ion, which acts as a catalyst. So that ion that acts as a catalyst then is able to destabilize ammonia borane and able to now create the reaction at temperature, again, around 80, 90 degrees, around 85 degrees C, lower than PEM fuel cell temperature once again. And what you find here is that these are some other catalysts that people had used in the literature when we did our work. Only boric acid is the one that has almost an instantaneous reaction by the time you hit the 85 degrees C. So temperature is increasing the reactor. By the time that reaches the set point, all these other catalysts, while they're attractive in the sense that they will begin to release hydrogen at temperatures even lower than 85 degrees C, yet they're not sufficiently active because they just plateau out, fizzle out by release of around 3, 4, 5% hydrogen. That's the end of it. No more. Boric acid is the only one that actually can generate huge quantities of hydrogen from the ammonia borane. So then we also, of course, did some analyses of the products that came out of this whole spent reaction, because one of the things is that you have to be able to regenerate the product, and that is actually the key. That it turns out that the process still is unfulfillable in the dream, is that you need to be able to regenerate the spent product commercially at high efficiency, low price, back to ammonia borane, so that the keep on using it all the time. That is where the process remains still. So we're able to test actually by solid-state NMR techniques that indeed if you did, for example, without the heat management, then you are getting NH2BH2 product out, which means one hydrogen came out, and what remains is 2 hydrogen inside the system. Whereas if you did with heat management, also of course if you did it with boric acid, your products are actually NHBH, either linear or cyclic. So indeed, by confirmation of the product NMR structure, you can tell that you did release the 2 moles of hydrogen because your product that remains has only 1 mole of hydrogen, NHBH kind of structures. So through various kinds of figuring, you can see that things are working. And in fact, this summarizes what I have just talked about in different systems. If you did neat thermolysis, you'd have to go to much higher temperature to release 2 moles. Hydrothermolysis will do it, but the problem is you get BO bonds and you get huge amounts of ammonia. You cannot do it. But thermolysis will give about 10 ppm and again 5 to 10, 15 ppm with boric acid. So these are 2 viable processes by which we can generate at PEM fuel cell temperature hydrogen in the amounts that are needed to fuel a PEM fuel cell car. But the trouble still remains how to regenerate the thing. That is where the problem remains. And then at this point, because the time was moving on, and so if I just summarize these things, this chart produced by DOE, this is rectangle is where you want to be. 2017 is the last that they have. You need to be above this region here in terms of the weight produced, hydrogen produced, and the ultimate is 2025, you need to be above here. So our 3 methods actually are quite high in the rectangle. In fact, if we account for the weight of water in hydrothermolysis, or the quartz wool, or the boric acid, they come down, but yet there is quite a bit of gap still in the system. So from the point of view of performance, we can do it, but it's the regeneration that still keeps the problem from being solved fully. Of course, then people want to make cars and they want to sell cars, and so what's the status today? Well, so DOE closed the system, closed the funding for these directions about 3 years ago, and said, okay, we will just now at the moment focus on just generating cylinder hydrogen so that at least cars can be made and they can be tested. In fact, I should first say that these are some papers, about 15 or so, that came out of the work that I just talked about. And they went on till very recently, and a couple of patents also came out. There are some more that are in the process, but these are actually issued patents. So, and the blue ones, for those who may be strongly interested, are the ones that are more strongly recommended to be read. But here are 4 cars, actually. I just made this slide over the weekend. And these are cars actually you can buy. You can buy them. In fact, their prices are even listed here. 63, this will be sold in 2000. This is available, these 3 are available right now today. This will be available in 2017 model, 76, the Mercedes, Toyota, and so on. And they all have this 10,000-pound cylinder hydrogen inside them. So you can buy these cars, you can run, but hopefully there will be a time again when DOE will decide to fund for research related to this. And in fact, the next research in my own mind needs to be on the regeneration side, because I think we have systems, but now we just need to do regeneration. Okay, all right. Now I want to go on to the topic number 2, at least. At least we finish one more topic, if not all 4. And maybe there'll be lecture number 2 some point in the future. This brings me to a very brilliant student, Danny Gao, who I had the great pleasure to work with for her PhD. And again, she finished in about 4 years her PhD and is working with Shell. And Yang Xiao, who is actually sitting in the background here, who did a PhD jointly with me, but only the last 2 years of his PhD were with me, and the rest of his PhD was from Southeast University in China. And he was fortunate, and I was fortunate that he got this nice China Scholarship Council 2-year fellowship for completing the PhD here. So the PhD degree is from Southeast, but he has a number of papers with me as part of his PhD. And then he stayed on as a postdoc and is looking now for his own faculty position starting this coming fall. So Danny Gao and Yang Xiao had worked on this problem, catalytic upgrading biomass. So this problem is, I think, all well known to many of you. The second generation biomass is using wood, corn stover, and things like that in order to produce first to fast pyrolysis, for example. There are many ways of doing these things, but one method is to do fast pyrolysis to produce something that looks like actually oil, petroleum, but it's not. It looks very much like oil. It's not. The reason it's not is that it's very high oxygen content, about 35 to 50%, in fact. Very high oxygen content. In normal petroleum is less than 1% oxygen. So the oxygen needs to be removed from the pyrolysis oil that's come. So one can do upgrading of it through catalytic and other means. Now, the trouble is, of course, if you look at pyrolysis bio-oil and say, well, okay, it has about 400 compounds. If you start doing its upgrading, and upgrading will be by hydrogen or by some other reductant. If you do that, 400 compounds, what are you going to learn out of this from a student's thesis or mechanistically? Maybe you can make a process out of it that somebody could use, but you couldn't. So basically, what many people do, including ourselves, is to select a model compound and to work on a model compound. So we and others have, many of us have focused on a compound called guaiacol. I'll show you its structure in the next slide. So this model compound is not without significance inside these 400 compounds, because it is actually the one, these polyols, these come from lignin thermal degradation. And it turns out that they are the largest component of those 400. In fact, about 35% of the pyrolysis bio-oil contains the same basic methoxy and hydroxyl groups like guaiacol does. So it is a very representative compound. If you're going to work with a representative compound, it's the one of choice. So we chose that as well. So guaiacol, here is guaiacol, very simple structure. So here is something you can study actually in the laboratory, and don't worry about it. If you have 400 compounds to start with and you start doing some reaction with them, you will produce 2,000 compounds right away. Just their analysis is a nightmare, and if not impossible. So to do anything useful is very difficult, except to create nice processes, which we need to do, of course. So it's abundant, it's representative. It's also a source of deactivation because the methoxyl group, actually, deactivation of the catalyst. So we used 4 different catalysts: ruthenium, rhodium, platinum, and palladium. And we said, good, we're going to start studying them. We're going to do hydrogen treatment, and we're going to try to reduce the hydrogen content and see what we get out of it. So we did. We made a nice setup here, and so on and so forth. So one way to check is that, are you reducing the oxygen level when you're doing the hydrogen treatment? Well, so guaiacol, when you start off with you're here, so after some treatment, this is after about 60 minutes or so, then you indeed have reduced. So indeed it's working. You're doing something useful. If you look at the lowest levels, they are for platinum and for ruthenium. So platinum and ruthenium are good catalysts. In a reasonable amount of time, they will reduce the oxygen level. Good. Now you start looking at this. This also is as a function of time now, what's happening to conversion of guaiacol as a function of time. And these are the 4 catalysts. These are standard conditions, by the way, in which we were testing these things in the laboratory. Because you've got to make some standard conditions to test everything under. Reasonable conditions. So what you find is, interestingly, platinum has reasonable activity, around 90% conversion, and relatively steady over time, say 5 hours. Whereas all these other catalysts were deactivating rapidly. So therefore, it's good to reduce the hydrogen level. It's also stable. And you can do it at a high level, 90% actually. So pretty good. Good thing to start with. So we said, good, select provides highest stability. This is the product distribution out of the 4 catalysts. One thing, and these are different things, I won't run through them, but some of the lower ones are actually gases. So when you do the hydrogen treatment, you're also going to make some gases, actually. But at the end, what you want is the liquid products, because those are what you're going to sell. If you make CO and CO2 and methane, they're not very useful to sell. But you want to make liquid products, chemicals or fuel type that you can sell. That's what you want. The blue one is a big one here. Blue one is phenol. What you find is when you do hydrogen treatment of guaiacol, you make gobs of phenol. Phenol, actually, if you're going to make a compound, phenol basically from guaiacol is just when we take away the methoxy that's gone, what remains is phenol. It's actually pretty good. Phenol is selling, as I checked over the weekend again. I guess I was doing a little bit of work on the weekend. It's about 50 cents a pound, actually. Gasoline is about $2.50 a gallon. If you convert that in terms of cents a pound, it's about 40 cents a pound. So if you're going to make something out of it, chemical is a little better. Making phenol is a little better than to make gasoline, for example. You can make a little more money if you make phenol, actually. Okay. And there are other compounds, too, that come out. This green one is actually cyclopentanone, and this one here is catechol. So platinum produces other valuable compounds also, other than just phenol. So we wanted to then understand, why is it that platinum was not deactivating with time while ruthenium was? And of course, these other ones too. So let's just take the extreme one. Ruthenium is the most deactivating. So let's just try to understand what the heck is going on with ruthenium versus platinum. Why is it that they are different, actually? So we said, okay, so one thing that can happen is with catalysts, and people who work with catalysts know this, that these are some TEM scans, and you see there are 2 to 4 nanometer particles. So they're very, very small particles. They're supported on the activated carbon support, but they can migrate and they can then coalesce with each other. They can make larger particles, and so basically they could sinter. And so you could lose activity, and you could lose, maybe deactivation occurred because of sintering process that is well known to metallurgists like Arvind. Yeah. Sintering process. But then it turns out that if you look at the used versus unused, they're about the same size distribution. There's really not a sintering problem. Sintering did not occur. And also the temperature is relatively low. It's only 300 degrees C. You don't sinter platinum at 300 degrees C. Yeah, 700 you could, but not 300. It's too low. So then the only thing you could imagine is some deactivation occurred by coking. So some coke deposit occurred, okay. So then to analyze that further, what we said, okay, good. Let's take both platinum, used platinum carbon, and take used ruthenium carbon. And let's dissolve out what is deposited by dissolving in a solvent, dichloromethane. Let's dissolve it out. And let's try to analyze what you've got. So when you do that, you find that the ones that are coming from platinum carbon deposit, they are linked ring compounds. They have a different kind of structure as opposed to condensed ring compounds that are coming out of the ruthenium. So condensed ring compounds, well known in the petroleum refining literature, are the ones that lead to coke, actually. These do not lead to coke, these lead to coke. So the difference is coming from the analysis of the dissolved compounds that it is actually the nature of the coke deposit that caused the difference. And that also was confirmed by TG analysis. So if you take platinum carbon and the fresh one versus used one, and you take the difference, then in the platinum case, the deposits came out much sooner as compared to ruthenium, which they came out at a much higher temperature. And these are less strongly adsorbed, so they come out sooner at lower temperature when you heat them up. So we're heating up in a TGA from normal room temperature to actually 1,000 degrees C and monitoring the weight change. So both by analysis of the dissolved compounds and by TG analysis, we can tell that it is the nature of the deposit that caused the deactivation in the case of ruthenium and did not cause a deposit in the case of, and there are some kinetics of the reactions. I think that I should be finishing just in a couple of more minutes, right? Okay. So I do want to finish this topic at least fully, if you give me the liberty. I shouldn't have said those stories in the beginning, and stories take time, but they're important for life, so I think stories are important. So if you heard from me 2 topics instead of 4, that's plenty already, I think. Maybe too much already. All right, so something about kinetics. So we were able to, I won't go through the detail, but we were able to establish, for example, that it's good to do 300 degrees C, because if you increase the temperature, you increase the conversion, but the problem is that you're making more and more gas then. And the liquid fraction, which is around 70%, is the highest, about 300. So beyond 300, you'll get more conversion of glycol, but you're making gas out of it, so it's useless, actually. Don't do that. So why waste your money and time to make something that you don't want? Then we did some kinetics, also the pathway analysis, just how was the reaction occurring, and the kinetics of the reaction established all of that. So this is guaiacol. It turns out that guaiacol makes catechol. Guaiacol also directly can make phenol and cyclopentanone. We observe all these things when we do the experiments. Then it turns out that if you start the reaction with catechol itself, you can actually make cyclopentanone and also phenol from it. So catechol will react to make this as well. So the network is actually this. This is the network. And we were able to decipher the kinetics of the reaction network in a paper that came out last year. And these are kinetics, and these are the experimental, the modeled kinetic fitting now of the data that says that we know something about the kinetics, actually, because the curves are passing quite reasonably well through the data. I will finish just these 2 slides now, finish the talk with this, because these are the last 2 slides related to the guaiacol problem. And they have to do with the fact that we should keep thinking, of course, as we solve problems, of how to actually do it better. So we know that we can upgrade guaiacol and hopefully all of bio-oil really through hydrogenation, hydrodeoxygenation. Many, many papers exist on these, including our own. By the way, Danny's paper, the one that I just mentioned, came out only 2014, is really rapidly getting citations. In fact, her paper, even at the ASUG meeting, won the Best Paper Award for the catalysis and reaction engineering session, actually, out of, I don't know what, 100 or whatever papers that were given. So her paper was pretty good, actually. So I was very fortunate that she worked with me. But we have to keep on improving, in our mind always. And so we can do with hydrogen, but hydrogen is expensive to produce hydrogen. So why don't instead, so a couple of years ago I had the idea, actually not even 2 years ago, I think it was in around April of 2015, I had the idea, well, why don't we use some other reductant, a cheaper one, like methane. Methane is available in natural gas, is 95% plus. Plus is available in shale gas, 70% plus. In fact, I think that Jeff Miller was here, and Fabio is here. Fabio, Jeff, and some of us are participating in a ERC proposal for converting shale resources into more valuable things. And part of that problem is the methane, is to how to convert methane. So that's to make other chemicals out of it. But here is the use of methane, because there's so much available in natural and shale gas, to use as a reductant, a much cheaper reductant than hydrogen, because you don't have to make it. It's available to us cheaply, very cheaply. So this I had an idea in April, and I had Yang Shao work on it. I said, Yang, I think I got a good idea, I think. Let's try to work it out in the lab. In about 2 months, he produced very nice research. Then we sent it out for publication, and it was accepted in about 4 or 5 weeks, and I think in about 3 or 4 months after the initial idea, the paper already was out in the press, actually. It was one of the fastest papers I've had, I think. Anyway, so it turns out that, to make a long story short again, I had worked with platinum bismuth catalyst. So platinum, you need something more than platinum if you want to use methane, because then methane deactivates, it turns out, again, because of the breakup of methane into methyl radicals, and they will break to carbon then. So it turns out, and here I think I may have to stand because I cannot read so clearly. If you see here, I don't know if you can read it correctly, but this is platinum hydrogen. So we have about, what, 90% conversion going on, and time on stream stable. Now, if we just take platinum and now put methane instead, then you actually get this red line here, red curve. So initially, not bad. So methane reduces the activity a little, because at the same time, you have to increase the temperature to get the same activity. But because of the deactivation, you have a problem. You cannot keep on doing this. You've got to do something to your catalyst. So you can add bismuth to the catalyst. So when you add the bismuth to the catalyst, and I will not go through lots of reasoning here. So if you just use hydrogen alone now, you get this sort of bluish color. So it reduces the activity of platinum because now some bismuth is added, so it's now covering some sites of platinum, so it's not so much platinum available to you. But of course, it is stable, but reduced activity. So you would not add, for hydrogen, you would not add bismuth to platinum, actually. But where it really helps is the last one, which is the platinum bismuth and then methane. Now it is stable, you see? Now it's stable all the time. So addition of bismuth permitted the use of methane as a reductant instead of hydrogen. And the mechanistic steps here are that for the methane deoxygenation, you actually make ethane, because you make methane splits into methane and hydrogen, and the hydrogen does its job. And then the methane, the two methanes will join together. Of course, they will break up further to make carbon, but they will also join together to make ethane out of it. So that's why you get ethane. And in fact, you see ethane in the product here. You can see this red is ethane actually here. You get the same kind of product distributions in the two cases, platinum hydrogen or platinum bismuth hydrogen versus platinum methane or platinum bismethane. The difference is that here we have now ethane, whereas there we had methane coming out. That's the only difference. And then again, we can do kinetics and so on. This was the paper I was mentioning to you that came out very, very rapidly in the journal. Took time. And of course, then we got the kinetics for this reaction also, and so on and so forth. So this does finish this part, at least the two parts of my talk. And I could not start the third and fourth. They are actually shorter, it turns out. If we had 20 more minutes, we could do them, but then we don't, and I won't. But I hope that you got the impression of a few things. Number one, that really we have some outstanding graduate students and postdoctoral students at Purdue. They do remarkable work. As faculty members, we are very fortunate to be what we do. We have the presence of these young people who work with us, and in some cases, we give some ideas, but most of the time it's the reverse. We get ideas from them, and they do lots and lots of very good things. I'm very grateful to all these students who have worked with me and postdocs over the years, and my colleagues who inspire me on a daily basis, and I'm seeing a number of them sitting here. I'm so thankful to them that they are here, first of all, but not here, that they are in the building Forney Hall, where we all are together, and where we all do good work. We respect each other. We have great admiration for each other. There is no squabbling, fighting going on. We are working together with the sole goal of making our school, Purdue Engineering, and Purdue better. I am so fortunate to have been a part of this whole journey. Thank you very, very much for your attention. Thank you.